So we've seen how we can construct PV diagrams to describe different kinds of processes. Let's now take a look at how we might actually determine the heat or work that's generated in those processes by looking at a couple of examples. First, let me remind you that from the first law, we have that the change in internal energy is going to be written as a sum of contributions from heat and work. And in the case of work, we're going to confine ourselves to mechanical work. So PV type work that we're going to talk about here. Now, we've also seen that we can impose constraints of different kinds, and those can sometimes lead us to immediate conclusions. So let me illustrate that. Isochoric changes, which involve constant volume, are ones where, since constant volume, we have no change in volume, which means that the work for such a process is going to be zero. This also means that the incremental change in internal energy is all due to heat at constant volume, and that the change in internal energy is just that heat at constant volume. We've also seen, by the way, that this means that this change can be written in many cases as the heat capacity at constant volume times the change in temperature. And in fact, this particular result is going to be true for ideal gases no matter what. So for ideal gas, this is always true, no matter what the process involves, whether it's a constant volume process or not. All right, what about an isobaric process? Well, in that case, the constant, that the thing that's being held constant is the pressure. So now we have that work is equal to pressure times the change in volume. And we might also write that, oops, sorry, I left out the minus sign. Don't forget the minus sign. So that might be equal to minus P times V2 minus V1. Now, the change in this particular case is going to be dictated by the equation of state. So if we're dealing with an ideal gas, then we would simply have that the temperature here is going to be the pressure times the volume over the ideal gas constant. I will say that implicitly here I've assumed that the number of moles is 1. We will generally see this in most of the problems that we'll deal with. If it's not 1, it will be specified, and then we'll include it in our equations. But for now, we'll just let it equal to 1, so we can write temperature is equal to PV divided by R. All right. So when we have an isothermal process, what does that mean? So T is constant, so delta T is going to be equal to 0. And when delta T is equal to 0, if it's an ideal gas, remember I said delta U is going to be equal to this, but that's just going to be 0 for an isothermal process. So for isothermal processes, we will generally find that ideal gases have the result that delta U is 0 in an isothermal process. All right, other things though will not be 0. So since delta U is equal to Q plus W, if this equals 0, that means that Q is going to be equal to minus work. So we only need to calculate one of the two in order to get a result there. Let's see an example of that. Let's suppose we have an isothermal expansion. And the isothermal expansion will take us at constant P, or sorry, not at constant P, from V1 to V2. Now we know from the ideal gas equation of state that we can write the pressure as a function of volume. It will simply be R times T divided by V. So now calculating the isothermal expansion work is just going to be a matter of evaluating the integral from point 1 to point 2 of P of V dV. But we have P of V written over here, so we can simply write this as minus the integral from 1 to 2 of RT over V times dV. Now the RT are constant. Temperature is constant in an isothermal process, and the gas constant is constant. So I can pull it outside the integral. It's not going to play a role in the integral itself. So I'm going to be left, anticipating the result already, I'm going to be left with an integral that looks like this, dV over V. Now, hopefully you remember from calculus that whenever you have an integral that looks like this, the result is the natural logarithm of x. And if it's evaluated between 2 points A and B, I'm going to evaluate that from A to B, that it will be log of B over A. All right, so we're going to be using those results here to simply write that the isothermal work is going to be R times the temperature of that isothermal curve times log of V evaluated from V1 to V2, and that this is simply going to be negative RT log of V2 divided by V1. And I'll remind you that we got up here that heat is equal to negative work, so this is negative heat. So in one stroke we have actually evaluated both the heat and the work for this process, but simply because we have that delta U is equal to 0 in an isothermal process. All right, now I want to shift gears a little bit and talk about what happens when we have more than one step. So we're going to talk about a process of 2 steps. Now, when we have a process of 2 steps, we still need to calculate things for each step, but the total process, that is the sum of the 2 steps, is going to simply be the sum of those 2 steps. So the total change is going to be equal to the sum of the changes in each step. So I want to imagine a process that has the following 2 steps. The first step is going to be an isobaric expansion that goes from V1 to V2 at pressure P1. Isobaric, so it's constant pressure. This is the constant pressure. And the second step will be an isothermal compression from the endpoint of the first step that goes back to V1. So an isothermal compression that goes from V2 to V1. So how will we deal with this? Okay, well, first of all, let's draw it on the PV diagram so that we can see what we're talking about. So here's pressure, here's volume, and we're going to start at some pressure down here, P1, and some point here that represents V1, and we're going to undergo an expansion over to V2. All right, so that's the first step, isobaric expansion. The second step is going to go back to V1, but now that since it's an isothermal thing, we're going to end up at a higher pressure, P2. And I'll try to draw this more carefully here. Okay, so that's going to be our isothermal curve. We call those isotherms. And this represents step 2 in the process. So we first go across from here to here in step 1, and then we undergo a compression up to the final point up here, which is P2 V2. Actually, V2 is V1, right? P2 V1. All right, so what happens in the first step? The first step is a relatively easy one, isobaric step. So that means that our work is simply going to be minus P times delta V, or minus P times V2 minus V1. Okay, it's the area underneath that first curve. All right, since we're going from left to right, it's going to end up being negative, as it's shown here. V2 is greater than V1 because it's an expansion. So this will be a negative quantity. All right, how would we calculate something like the heat or the internal energy? Well, the internal energy, I'll do that when it's a little bit easier. We know that for an ideal gas, it's just going to be the constant volume heat capacity times the change in temperature. But what is this change in temperature? How would we find that? Well, remember that for the ideal gas, the temperature is equal to the pressure times the volume over the gas constant. So T1 is going to be P1 V1 over R, and T2 is going to be P1 V2 over R, because P didn't change in that step. So I can find T1 and T2 and use that to calculate delta T. And once I have that, then I can use these in this formula to determine what the internal energy change is. Finally, I could find what the heat change is because I know that heat plus work is equal to the internal energy. So if I just take that internal energy and subtract the work, I'll get the heat. All right, so in fact what we would find is that this would give us negative P times delta V, but we're taking negative work, so it's going to end up being a positive, and then I add that to my CV delta T, so my total heat change would be given by this set of constants. What about the second step? Second step is isothermal. It is a compression. Okay, on the previous page we already calculated what the work is. The work is minus RT log of the final volume over the initial volume. In this case the final volume is V1 and the initial volume is V2. Alright, what do I know about an isothermal process? I also know that delta U is equal to 0. So that being the case, Q is going to equal negative W. So this up here is equal to negative Q. So now I have calculated W for each of these steps, I've calculated Q for each of these steps, and I've calculated delta U for each of these steps. Now if I label these by their step numbers, so for example this one I would call this W1, this one's W2, this is Q1, this is Q2, what will I have? Well, for the total process now, I'll have work total is equal to work 1 plus work 2 is equal to minus P1 times delta V, and work 2 is minus RT log of V1 over V2. So this will be my total work. My total heat in the process will be Q1 plus Q2. Okay, Q1 is going to be my delta U minus W. Delta U is CV delta T, and W was this minus PV, so it's going to be plus P delta V. And the Q for the second process is just minus the Q minus the W, so it'll be plus RT log of V1 over V2. All right, so when I add these two together, notice that these terms will cancel and these terms will cancel. So delta U, which is going to be W total plus Q total, will be simply CV delta T, and CV delta T is actually just the delta U for the first step. The second step, because it's isothermal, has delta U equals to 0. So this gives you a little bit of an illustration of how one can do this for a multi-step process. I hope this makes sense because you'll get a chance to do some of this on the problem set and in other venues.